All right, so let's start today by summarizing what we have learned this semester. That is, it's been a while since we've uh, completely written down our toolbox. I think that's probably a good thing to do. So, we started the semester dealing with kinematics. That is the study of how things move. If acceleration is a constant, we were able to use the definitions of velocity and acceleration to produce three kinematic equations. First, the velocity is going to be equal to the initial velocity plus a term due to acceleration. Second, the distance traveled is going to depend on the acceleration of the object, the initial velocity of the object, and the initial position of the object. And if you take 1, solve it for t, and plug it into 2, you get the time-independent kinematic equation. Next, we took a look at why things move, that is, the study of forces. And we've got one real workhorse here. We have the sum of forces equals ma. And this is Newton's second law. We also have some other kinds of forces that we learned about. It's kind of some specifics. So, for example, we learned how to deal with normal force, frictional force, in fact, let's maybe write those separately. So normal force, we usually denoted with a lowercase n. Friction was along a surface, and its magnitude was equal to mu n for some constant mu between 0 and 1. We learned how to deal with tension, which always points toward the middle, right? Which always, and we learned how to deal with centripetal. Right, which is the force required to stay on a circular path is equal to mv squared over r. We also studied energy. We got to our study of energy by considering what it looks like if you apply a force over a certain distance. We said that a force applied for a distance is work, and that work causes a change in energy. We have since learned a few specific kinds of energy that can be derived from a few different kinds of forces. We have, of course, kinetic energy. We have gravitational potential energy near the surface of the Earth. We have spring potential energy, which is the energy stored in a compressed spring. We have rotational energy. Next, we studied momentum. A force applied for a time rather than a distance provides an impulse which causes a change in momentum. And momentum we defined as the product of mass and velocity. We later revisited this when we talked about rotational motion, because rotational motion, a torque applied for a time, causes a change in angular momentum. And angular momentum is moment of inertia times angular velocity. Speaking of which, we did spend some time learning about rotation. The main thing in rotation is a change of coordinates. So an angular coordinate corresponds to a linear coordinate divided by the radius of the circle that we are rotating in. The most important concept here is torque, which is a force applied at a distance from a possible axis of rotation. We realized only the perpendicular part of this force that is perpendicular to what is called the lever arm counts. So force that is directed toward the center of mass causes translation, and force that is applied perpendicular to the direction to the center of mass causes rotation. And there's a version of Newton's second law for rotation. Possibly the most interesting thing from this section is that the moment of inertia of a point is equal to mr squared, and this came from a reorganization of Newton's second law, and that the moment of inertia for some larger object is just the integral over all of its points. All right, any questions, clarifications, comments thus far? Right, because this is the summary of everything we've done the entire semester so far. Okay. So what I would like to do today is actually to start talking about um, a concept called elasticity. So this discussion is part of an attempt to make what we have talked about apply to more realistic, like real materials. For example, we have previously talked about tension as a force. So if we have a pulley and a rope going over the pulley, mass is attached to each end of the rope, larger one on the right. In the beginning of the semester, we analyzed this problem and we said that uh, we said, all right, sum of forces on this system is equal to ma. And there were a couple of ways we could have gone about uh, analyzing this problem. But the simplest way is to say, well, rotation, like this direction is positive. So the only forces that we have here are m2g pulling the system in the positive direction, m1g pulling to the left, so in the negative direction. Add those up, and we have the total mass of the system times the system's acceleration. All right, so the system's acceleration is then equal to m2 minus m1 times g over m2 plus m1. That was the very beginning of the semester. It was a very simplified analysis. We left out a number of important things. Later, we realized, like, hey, the pulley itself also has some mass. And if we want this whole system to rotate to the left, we have to also take into account, the force like rotating the pulley. Uh, so when we did that, we came to we had to do a couple of things. First of all, the pulley is approximately a disk. So we were able to calculate that the moment of inertia of the pulley should be about 1/2 times the mass of the pulley times the square of the radius of the pulley. And then we were able to say that the torque on the pulley was caused by the tension in the rope. Right? The tension acts perpendicularly to the pulley, so all of its force counts. And this is what Newton's second law for the pulley looks like. Is everybody with me when I write this down for the pulley? Then you have comments, questions on this analysis as we're beginning. So we used Newton's second law for rotation, wrote down what the effect of the tension in the rope must have on the pulley, and we could even we could go a little further, divide both sides by the radius of the pulley, solve for tension. So one of these r's go away, and in the other case, we can recognize that r times alpha, right? So the radius times the angular acceleration is equal to the linear acceleration. Right? This gives us two unknowns, and then we're able to, say, do an analysis on the second block as well, right? M2. So we have T minus M2G equals M2A. And similarly, for the third one, we could write oh, this should actually be reversed. Here we go. Right, there's a few different ways of attacking this. But maybe one way we want to do that is just to add all three of these equations together. So we get T minus T plus M2G plus T minus M1G equals, on the other hand, every term has an A in it. Factor that out. Get M1 plus M2 plus 1/2 mass of the pulley. Not too deep. So we just get T equals, or T rather, plus M2G minus M1G and we could use any one of these expressions to eliminate T from this if we wanted. But the point is that we refined our analysis in such a way that we now took into account the physical characteristics of the pulley rather than saying that the pulley was just some mathematically perfect object. And our conclusion was that the mass of the pulley counts for half. Like half of the mass of the pulley counts when we are talking about the entire like mass of the system. All right, so today we're going to refine that um, even one piece more. So we previously had talked about the pulley as a real object. Today we're going to talk about the rope as a real object. So far in our analysis, we've assumed two things of our rope. One is that its length doesn't change. And two, that it doesn't slip at all when it's causing the pulley to rotate. The second one is beyond the scope of this class, but there is a relatively simple way to deal with the changing length of the rope. Now, why does the rope change length? Yeah, if you pull on a rope, it stretches a little, right? So consider there's like a range of things that we could think about that are all doing this basically the same job. If instead of a rope we had a slinky, we imagine that if we pull on it, it stretches a lot. If we have a rope, we pull on it, it stretches a little. What if instead of a rope we had a steel beam? It's the steel rod. What happens if you anchor one end of a steel rod and then you pull on the other end? Does it stretch? Maybe very minuscule. That is the right answer. So stretches very little. But in fact, all materials respond to stress, that is being pulled or squished. They respond to stress with strain. So stress is the pressure you apply and strain is the resulting deformation. So all things deform when you apply pressure to them. So let me share a video with you guys. Since we're talking about things deforming. I'm going to all right. Anyone watched hydraulic press videos before?
And all are same diameter and length. And under the metals, we have our 150 tons force sensor, so we can see how much force it takes to flatten the different metals. And I'm not sure can we flatten these, but at least these three are going to go pretty flat. And I think we are going to start with the copper. Okay, so here we go with the copper, and it's...
Can everyone hear? So what do you think is going to happen when we apply this 100-ton press to this cylinder of copper? Squish. That is the correct answer.
It's the heaviest one of all the metals, but I think it's not going to be the hardest. But let's see. Uh-oh, uh-oh.
Broke his press.
Yeah, it starts to bend, but I think we are going to declare the point where it starts to go, because it's like now, now at the moment. It's really weird. I think it's going to be hot. It's like, it's not super hot. And
all right, skip ahead, mix metal.
I think it's going. We have to go have a look. It's just started to go, and I think if I would keep going, then it's going to get like twisted again.
So of course it's going to keep going. Look at that again.
Okay, so now without the sensor, and we are going to try first the brass. I'm not sure is this already too bent, but we are going to try.
What the?
That wasn't good. We broke the window from the shop. It went through all the windows.
It went through all the windows. Not, I think the last one is intact. Yeah, the last one is broken, but not all the way through.
Ooh.
So we weren't exactly expecting that last bit. So I like this video because it shows actually all the three things that we're going to be concerned with when we talk about deformation. So there are two kinds of strain. if we have elastic strain, it would also help if I could spell elastic. If we have elastic strain, then if we stop applying the stress, it'll go back to its original shape. So release the stress, right? And then deformation goes away. So this is the kind of strain that you see when you tug on a rope, right? So if you tug on a rope, it stretches a little bit. And then if you stop tugging on the rope, it goes back to its original length. The other thing I want to note about elastic strain is more stress leads to more strain. So if we're dealing with real materials here, if we apply a force to an object and it can't move, it's going to deform. And higher levels of deformation require higher levels of force. And if you stop applying the force, it goes back to its original shape. What does that sound like? We have studied something that behaves like that already. So what have we studied where the force and the deformation are directly related, and if you take away the force, you take away the deformation? Yeah, springs. That is right. So we didn't study springs on accident. We studied springs because they are a model for all real-world materials. So in a moment, we are going to expand our model of springs to include the behavior of real-world rigid materials. Something like nitinol, the memory titanium, you explain it exactly that way. So the nitinol also wants to go back to its original shape if you've deformed it. The difference there is that you lock in the shape by applying heat. Right? But that's a little bit more complicated. However, Engineer Guy's got a great video on that. So I'll link that to you later. The other kind of strain that we observe is plastic strain. And plastic strain does not revert. So you notice when we were watching the hydraulic press, when he squished the copper cylinder, it stayed squished even when the press was removed from it. And the point at which a material will switch from elastic to plastic strain is different for every material. And so one of the things you can study if you become a materials engineer is the elastic plastic transition. So when does a material go switch from temporary deformation that will bounce back to permanent deformation, and that's a rich field of study. The last thing that we saw in that video is failure. So different materials will have different failure modes. So typically, a small amount of stress will produce an elastic strain. A larger amount of stress will produce a plastic strain, and then a huge amount of stress will produce a failure mode. And in this case, the failure mode was the whole thing just cracked and part of it sheared off. Right? This elastic-plastic transition is also called the yield strength of a material, and the transition to failure happens at the ultimate strength. All right. Do we have any comments or questions before we move on to the mathematical description? Also, Cortez, here's your link. Okay. So let's start with the simplest deformation. If we have a rod which is fixed at one end, and we are applying some force to the end of it. How is this object going to behave? Well, let's put F on one side and build up a kind of qualitative expectation on the right-hand side. So we expect that we will cause some deformation in the length of this rod. So there'll be some amount of change in length. What sort of characteristics do you think would make this rod easier or more difficult to deform? Right, so if the rod it was thicker, would it be more difficult or easier to deform? Is it easier to squish something that's thick or thin? thin is definitely going to be easier to squish. So thicker means harder to squish. And what do we mean by thicker or thinner in this context? Well, usually we talk about that in terms of the cross-sectional area. So larger area means more force required to make the same deformation. What about the initial length of the rod? Is it easier to squish it by a little bit if it's quite long or if it's quite short? All right, so is it easier to squish a rod by 1 centimeter if you start with a rod that's 10 centimeters or if you start with a rod that's 10,000 centimeters? All right, we've got one guess. So shorter is easier to squish, you think? So we have answers for both. We have shorter, longer, and maybe in the chat. Shorter is more condensed, yeah, yeah. Let's think about a spring for a moment. Let's say we had a spring and that's a terribly drawn spring. I'm going to try that again. Say here's its original length. And if we imagine dividing it in half, each of these kind of subsprings would have length L over 2. So then we stretch it. And it's got a new longer length. Right? Its new length is L plus some extra bit. And if we imagine dividing it in half, each of these halves have a length of L over 2 plus delta L over 2. Right? The stretch is distributed evenly among the two halves of this spring. So what is the tension in this spring different anywhere, or is it the same everywhere? So if you're stretching a spring, is the tension in the spring homogeneous? That is it the same everywhere? Or are there some parts of the spring that have a higher tension than others? right, let's let a few answers flow in. So count of 3, everybody type in either everywhere or everywhere, type in same or different. Okay, so type in same if you think that the tension is the same everywhere. Type in different if you think that it's different, that the tension is different in various parts of the spring. All right, so on 3, 1, 2, 3, go. All right, so we got about a 60% response rate. Most people are saying the same everywhere. And yeah, it is the same everywhere. So imagine if we had this spring split in two, if the front half was under higher tension than the back half, then the front half would pull on the back half and stretch it harder than the back half would pull on the front half. So therefore, the front half would then, contract, and the back half would stretch, and this would happen until they were both under the same amount of tension. Another way of thinking about it is by using Newton's third law, right? So the force of one object on another has to be equal to the force of the second object on the first. So if our two, quote unquote objects here are the halves of the spring, then the tension with which one is pulling on two has got to be equal to the tension with which two is pulling on one. Right? So Newton's third law says that they've got to be the same, and we can imagine that if it wasn't the same, the effect of the spring would be to quickly equalize. So if the tension is the same everywhere, for the whole spring overall, right? For a spring of length L, the tension has caused a stretch of delta L. But for a spring of length L over 2, it's only caused a stretch of delta L over 2. So this isn't something that we covered directly, but if you think about it like that, it means that if you chop a spring in half, right, so if we have one K value for the whole spring, one spring constant for this whole thing, then the spring constant for just one half of the spring is actually 2K. And in fact, if you have a bunch of different springs, possibly with different spring constants, you can add them up to get an overall spring constant. So the overall spring constant, maybe I'll use subscript T for total, is, so you add up all of the K's of the individual springs in reciprocal, and once you've added up the reciprocals, you take the reciprocal. So I'll leave you to check that this actually works for the cutting the spring in half. So the point of all this is that a longer spring is easier to stretch. Since we are modeling real objects based on the behavior of springs, we expect this to be the same for a rod too. So the longer that the rod is originally, the easier it is to stretch by a fixed amount. So L goes in the denominator because bigger L's means smaller forces required. So we are now missing only one thing from our model up here, from our model of how a rod will behave under compression. All right, what's the one thing that we haven't considered about our rod? Well, sure, it can break, but for our beginning analysis, we're going to say we're only compressing it enough so that it's still in the in the elastic region, right? It's in the elastic region because that's the region where it will behave like a spring. In the plastic region and the failure region, it's going to behave very different. Um, but yeah, but this region, the elastic region, that at least we can analyze. Right? The thing that we haven't considered about our rod, though, is what it's made of. Is it easier to compress a copper rod or a steel rod? Nobody has an intuition about what's stronger, copper or steel? Yeah, copper is much easier to squish than steel. So we're going to put in a fudge factor that covers material differences. Physicists do this a lot, right? We build the model based on logic, and then we add in a fudge factor and leave it for engineers to figure out. So we've got cross section. We've got length. And we've got a material fudge factor. I mean Young's modulus. So this is something that can be measured for a wide variety of materials. And if you look in your book or online, I like this website called Engineering Toolbox. But you can look up what the Young's modulus of various materials are. This isn't the form that we usually talk about stress and strain in, though. Instead, what we usually do is we divide the area over to the left-hand side. So we have force over area, right, which is pressure. And on the right-hand side, we just say we put delta L and L together, and we talk about a fractional change in length. which is sometimes written as sigma. And there's some advantages to writing it this way. The most important one is that we've grouped out like some of the dimensions that are specific to the object, right? So now we don't have to worry about cross-sectional area and forces. Instead, we just worry about pressure. Right. We have any comments on this? It's not the only way to deform a material, but the others, which are presented in the text, I strongly recommend that you read them. They're quite similar. So if we have a three-dimensional object, and we are pushing in from all sides, with a given pressure, then we'll have pressure equals the bulk modulus times the the strain, right? Fractional change in volume. You can also have shear strain, where you start with something that's nice and perpendicular, and you apply a force across its top, and you end up with something that is slanted. The thing that we're concerned with here is this amount of overhang. And we get, the pressure, we get a shear modulus now, and a amount of overhang as a fraction of the dimension. Okay. So that's all I wanted to cover today. If there are comments or questions, feel free to hang around and ask them. On Monday, we're going to spend pretty much the rest of the class working interesting problems that require multiple tools from multiple sections of our toolbox.